A binomial probability distribution is a specific type of probability distribution. This prefix bi here implies that we have outcomes in two categories. So we might be surveying people and asking them if yes or no about how they feel on an issue. We might be observing produced items on a production line and looking for whether they were acceptable. We would accept them or reject them. And in general, we talk about looking for a success or a failure. And then whatever success is whatever you're looking for. So let's look at the requirements then for a binomial probability distribution. And there are 4. The first is that our procedure has a fixed number of trials. So, as I said, if you're surveying people, you're surveying a fixed number of people. If you're inspecting items on a production line, you're inspecting a fixed number of items. If you are shooting at a target, you are taking shots a fixed number of times. If you're doing a medical study, you're looking at a fixed number of patients and looking for something there. Okay, so a fixed number. It doesn't just go on in an unlimited and unspecified amount of times. Okay, the second requirement is that the trials are independent. And we've talked about independence before in our probability section. And what this means is that the outcomes do not affect each other. The third requirement are that they're classified into 2 categories, that prefix bi, as I mentioned before. So if we were doing a medical study of people and we're looking for a specific gene that caused a disease, then that's our 2 categories. The person has the gene or the person does not. Or the person supports the issue or the person does not. Or the piston we're inspecting off the production line is defective or it is not defective. So 2 categories. And finally, that the probability of success is constant for each trial. So what that means is that the probability of a person saying that they do support the issue is constant. It's not like changing as you do your survey, or the probability that you have a defective piston on the line doesn't change during your procedure, or the probability that the patients you're studying have that gene for that disease is not changing during the procedure. So that's all that means. It's a fixed number, fixed probability there. And again, success is not necessarily a positive thing. You could be looking for a gene that causes disease, and a success is that you found that gene. We certainly don't think of a disease as being positive. So the word success is just what were you looking for. If you found it, that's a success. Okay. So recalled previously that we talked about independence and we talked about sampling with replacement. But when we conduct surveys, we're not going to replace the person back into the survey. We certainly don't want to ask the same person the survey. They certainly don't want us to survey them twice. So we always survey without replacement. And likewise, if you're inspecting pistons on the production line, or if you're studying patients, you really aren't going to make a selection and then put that subject back into the possible pool of subjects you would pull from again. So we have to be able to assume that these trials are independent. How can we do that if we are not doing our procedure with replacement? So that leads us to a guideline that we can use. And this is a way that we can treat dependent events as independent. And it's the 5% guideline for cumbersome calculations. Okay, it gets very cumbersome if you have to account for the fact that now you have one less subject in your sample and each time. So if we're trying to treat our dependent events as independent, we can use this rule. And it says that if a sample size is no more than 5% of the size of the population, we may treat the selections as being independent. Now that should be familiar. We saw this before in our discussion of acceptance sampling, and we actually said that if the sample size is less than or equal to 0.05 of the population size, if this is true, then we can assume independence, and independence is required for a binomial probability distribution. Okay, so now let's look at the notation we'll be using for our binomial probability distributions. Okay, notation. Alright, so as I said, in general we'll talk about success and failure. Are two outcomes that are required. So notation-wise, we could say that this would then be our probability of success, or lowercase p, probability of success. And we said that has to be constant throughout the trial. And then we'll have a probability of failure. But of course, that would be the complement of the probability of success, so it's just 1 minus p, and we'll often refer to that as q. But these are complements. You either have a success or a failure. There's no other possibility. Okay, so this is probability of failure. Okay, n is our fixed number of trials. And x is the specific number of successes in n trials. The specific number of successes in trials. Okay, so it will be between 0 and n, comma, inclusive. If you're running n trials, okay, you're going to inspect 50 pistons off the production line, well, then x can only be a number between 0 and 50. If success is a defective piston, you can only find a value between 0 and 50 for the number of defective pistons. You couldn't find 51, a number greater than n, and you certainly wouldn't find a negative number. But you could find 0 or n inclusive, so 0 or 50. Okay? And finally we have then the probability of x. And this is the probability of getting exactly x successes among n trials. The probability of getting exactly x successes among n trials. So if you're inspecting the pistons, you might look at the probability of getting 10 defective pistons among your total, say 50, that you're going to inspect. So what's the probability that if you inspect 50, you'll find 10 that were defective? That's what we mean by the probability of x. Okay, so now I want to mention that our textbook shows 3 methods for finding the probability, these probabilities corresponding to our random variable x. So I'll just note 3 ways to find binomial probabilities. And the first is to use the binomial probability formula. Oh, let's see. Doesn't look like an R is there. There it is. Okay. So which states? Let me see if I can. Let's get another color here. All right, the probability of x. So this is how we find that probability. This is one way, is to use a formula. The probability of x is equal to n factorial. Remember, n is our number of trials over n minus x factorial times x factorial. All of that times the probability of success raised to the x power times the probability of failure raised to the n minus x power. Okay, and we run this for x equals 0 to n. So 0, 1, 2, ... to n. Okay, so we can see all the parts that are involved in this calculation. Your sample size, the actual value you're looking for. So my example, the probability of 10 out of 50, 10 defects, as n is 50 and x is 10, right? So you're looking at a particular number of successes. Here's the probability of success. So that would be the probability of finding a defective piston in your inspection. And Q, the probability of failure, that's not finding a defective piston, so that'd be 1 minus P, right? And raised to these powers. So that's all the variables involved in calculating using the formula. We can also use use binomial probability tables. These have already been generated. They already use the formula based on some preset sample sizes, based on preset then x for each sample size. So when n is 10, your x's can be 0 to 10, right? So these are only for certain probabilities that they were able to do this. Only for certain p's. They couldn't do it for every possible one in the table. So certain ones are selected, and only for certain sample sizes. I think they only go from sample sizes of 2 to 15 in the tables that we have. Okay, and you'll find those in the appendix of the book, of your textbook. So I guess I'll make a note there in appendix. And then finally, the book mentions that we can use technology. Okay, so there's several of these. The main two that we want to be aware of are Excel and our TI 8384 / I'll just write that, technology. And so we'll primarily be using our calculators for finding binomial probabilities. So this table was generated using the formula. The technology is using this formula, so it's important to understand the structure of that formula, even though we will be using in our course primarily the TI 8384 technology.